Hello, this is the first session of Computational Electromagnetics, and we are going to first visit the equations, so the balance equations that we have for electromagnetics and Maxwell equations, basically, and then look at the numerical solution, which numerical method we can use, and how we can verify and assess them. So the first thing to look at is at the Maxwell equations. These are in fact, divergence-free conditions, similar to what we had in fluids, and the conservation form and the wave character of the equations will be also seen from how those equations derive from Maxwell's equations. So applications, they span from electromagnetic scattering, with many applications in biomedics and transport and detection also, and numerical solutions. So we'll see how we can face and the sensibility of the geometry that the solution have. So first of all, we will, which is the aim, okay, which is called computational electromagnetics, is solving Maxwell equations with numerical methods, and basically looking at the scattering, so whether we know the object and trying to see which is a scattered field, and more interesting, which is not knowing the object and from the scattered field trying to guess which is the shape or dimensions of the object. This, as you may guess, has many applications in biomedical, but then also in defense or in communications, etc. Right, so we have, okay, so to look at the how the objects behave in response to these electromagnetic waves. Some cases these are beneficial, and others may be detrimental to know inside an airplane how can be this field and how it's affected, or how the communications within the airplane are being also maybe disturbed by the presence of the object or by the geometry. So it's used also to assess how different objects are being modifying the electromagnetic field. As we have already mentioned, we have applications in biomedicine to see how our scalp is being affected by electromagnetic field. So there is a concern and a reasonable concern, and initially with those types of headphones, so the amount of energy and the power of the energy had to be assessed with regard to the electromagnetic field, so that no harm could be given to the receiver or the sender, etc. So one way of assessing is it's looking computationally how this field is being propagated and how being received by our body. There are other applications in bioengineering, so to detect cancer cells. Okay, so if we have, for instance, there's a difference in the stiffness or the material properties, and by looking at the scatter, this is detected as an external object with clear differences. So by the presence of this obstacle, we can see how the electromagnetic field is being also affected in order to detect this object. So this has applications in cancer detection or detection of any other tissues that have been also modified mechanically, and they also modify and perturb, okay, the magnetic field, electromagnetic field, and for this are all the scanners being used nowadays very often. So we are also, when we design a hovercraft, like in this case, so we will have some geometrical features as we have as an antenna, etc. We want that our communication is not being affected by the geometry or the presence of some engines as we usually have. So maybe when we talk about these communication systems, that's obviously also in all the Wi-Fi connections or the wireless connections also may be affected by the geometry. So we want to ensure that enough power is received to all the areas. It is not perturbed by the presence of any change in design, but also that it's not too much power neither, right? So one way of assessing is by looking at the computational field, okay, computed by the equations that we will see. And of course, also internally, there's many devices being affected by the presence of magnetic fields. Okay, we may have a power supply, which of course has transformers, and that also affects the remainder of our desktop, like in this case. Okay, so we talk about desktops or CPU machines, etc. How they are may be affected by the electromagnetic field. So with all that has also at the larger scale also to see magnetohydrodynamics. So how the transmission of the wave, and that may be with transmission with satellites, is being affected by the presence of a star. Okay, so this is the objective of magnetohydrodynamics. Okay, so the presence of a star. So how our communications may be affecting, or how the light, okay, as it travels, is being perturbed by this by the presence of this magnetic field. Okay, this happens when rays are being sent next to a star. So this is a simulation, okay, where we can see the flow. Okay, so this is the magnetic field, how it is visualized in this case. Okay, so this is the objective in many applications in astrophysics. So we the first thing to look is that these are the basic, very basic equations that we will deal with during the whole chapter. Okay, and this is Faraday's law, with in fact deals with the variation of the magnetic field that we have. So that's in fact flow, and we have the electrical field. So the presence of a field of electrical or magnetic field, in fact, are going to induce, okay, changes in the magnetic and electrical flow, B and D in this case. Okay, if there's no charge, okay, in the empty space, we have this J, which is the flow, which may be neglected without charges. If we have any charge, then we have also this electrical flow, okay, due to the presence of the charge. Okay, what they are in fact stating, these equations, is that whenever we have a field, and by field we mean the electrical, or also in this case, okay, that will be a magnetic field. Okay, so these fields they induce in fact flow in the magnetic field, and the magnetic field, so you have a flow in the electrical charges that we may have. So these in fact both electric and magnetic fields are both coupled. This is the first thing to note. So that the variation of the electrical field, and the fact that this rotational that we have here, as we have seen already in fluids, is non-zero whenever this field is rotating. So whenever we have a rotating electrical field like this one, okay, so the rotational in this case will be against towards inwards this whiteboard, right? So in other means, whenever we have some rotating electrical field, so we're going to have a variation of the magnetic flow. Okay, so this is what is being stated by this equation that we have. And similarly, when we have a magnetic field, because the presence of any magnetic field are going to have in the opposite direction. So in this case, I will be getting out of the whiteboard. So we have this magnetic field. This is going to create a variation of the electrical flow. Okay, so it means that in the presence of a charge, okay, that will be dragged by this flow, right? But even without the presence of the charge, this flow is there. The charge will be a way of detecting, but not necessarily we need the presence of these charges. The same happens here. Okay, if we have a magnet and we will place it here, will be in okay, dragged by this magnetic flow also here, and due to this rotating electrical field. So this is in fact the principles done by the engines whenever we have an electrical field that is in fact is curved. Okay, so we have this curve, so this induces a magnetic field that is provoking the rotation of the engine. So now very popular everywhere. Okay, and the same is being coupled in the other way around. So electric and magnetic fields, the two are being coupled. They are not independent of each other. And that was, in fact, the contributions of Maxwell, where we had the presence of this Ampere's law, okay, where we had, okay, we knew already the charges and the rotational of the magnetic field, they were coupled, okay, so it was also giving rise to this transient term for the electrical field. Okay, there's also a property, okay, which in fact is a consequence of these two equations here, right? So if we do the divergence of these two equations here that we have, okay, we can do the divergence on the two sides, and in fact the second, the divergence free conditions, follows. So because we would have that the divergence in the first case would be the divergence of our magnetic flow that we have will be equals to minus the divergence of the rotational of E. Okay, but this is always equals to 0 by the property of the divergence of the rotational. Okay, so this means that the divergence of B of the magnetic flow is equal to 0. And the same, we can do the same for the second equation. Okay, so the divergence of the electrical flow, okay, it's equal to the divergence of the rotation of the magnetic field, and this, for the same reason, is also equals to 0. Right, so these divergence-free conditions are in fact consequence of Maxwell equations. Nothing new, they can be deduced from here. Right, in the presence of these particles, so we need to add this flow, okay, due to a charge that is modifying, in fact, our magnetic field, and then the time variation of the flow. But in the empty space, we will, in general, neglect that if we're considering things in the field of in the outer space, but also if there's no charge condition that we may have. Okay, so there's these equations are not yet closed because we have the flow and the fields, and there's a relation, as we had in the constitutive equations for fluids and solids, okay, between the flow and the fields. Okay, in this case, this is given by the permeability for the magnetic case, okay, between the flow and the field. Okay, one is proportional by this constant, okay, which in the we will denote that in the empty space, okay, we will have an epsilon 0 and mu 0, okay, for the empty space. Okay, and the two of them are coupled. Okay, the two of them are coupled, and we will see how this coupling, okay, can be deduced, and they have a wave character. We also deduce why these equations give rise to wave-like solutions. Okay, and the two of them are going to oscillate and propagate with the same velocity, which is given by this. The inverse of the square root of the product of the constants, of the two material constants. Okay, permeability for the magnetic field, and then permittivity for the electrical field. In case that we have a charge, right? So, and that would be the conductivity given by the presence of the charge. We also that the flow is going to be to induce this flow due to the electrical field and this conductivity. Okay, because of the presence of the charges. We will see later where this velocity in fact is stemming. Right, so with these relations that we have in our Maxwell equations, so we have this B is by the permittivity multiplying by the field, Okay, and the same for the electrical field by the and this is permeability and this is permittivity. It looks a little bit all as a not just to false be a mistake, but these are the constants. So we have here the permeability and here for the permittivity. We introduce these constants in our relations that we have here for the Maxwell equations, and then if these are constant parameters, okay, what we have is that our mu multiplied by the derivative of h with respect to t is equal to minus the rotational of the electric field, and the permittivity by the derivative of our electric field, okay, it's equal to the rotational of the magnetic field. We will neglect all the flow due to the electrical charges. Okay, we will just work with these two sets of equations. This we mentioned that these are wave character, okay, and where in fact we should have a velocity that is given here as the product of these two constants. Okay, one way of obtaining the wave character of the equations, we have time derivatives, okay, and we have also spatial derivatives in here. So one way to have just one field, not that they are coupled as they are here, is to do for instance, the time derivative of the first equation and the space derivative of this equation that we have here, right? So in order to appear something like the rotational and the time derivative of h. So if we take the first equation and we do the time derivative, we will have that our permeability by the second derivative of the magnetic field is equal to minus the rotational of derivative of the magnetic field with respect to time, right? And on the other way around, if we do the rotational of the second equations, so we have epsilon by the time derivative of our rotational of the electric field must be equal to we have 2 times the rotational of the electrical field. We see that then these two quantities must be the same with the opposite sign, right? And then because we do have the same expression here, because we can swap time and spatial derivatives in this case. So we have that this divided by 1 over epsilon. Okay, so that mu must be equal with a minus to this term here. So we have minus and double rotational of h and minus 1 in fact over epsilon. Okay, we will put that in that side. Okay, then there's a property of something that anybody can check, is that the rotational, okay, it's equal to the gradient of the divergence, okay, the property of the operators, minus the divergence of the gradient. Okay, in our case, because the flow are divergence free, and by the constitutive laws, this is also equals to 0, right? So, and the divergence of the gradient is nothing else than the Laplacian, okay, of h, right? So with that, we end up having an equation that states that the second time derivative of my magnetic field is equal to 1 divided over mu multiplied by epsilon, and now the minus sign cancels with this minus sign by the Laplacian of h. And this is a wave equation for the magnetic field. We can do the same thing with space derivatives for the first Maxwell equations, for the first block, and time derivatives for the second block of Maxwell equations. In that way, we would obtain something exactly the same, but instead of H, with E, the electric field. So they behave with the same. This is the wave equation. Well, this is the speed. This is the unit. This has seconds square. So in fact, the speed will be exactly 1 over mu over epsilon. If you look in one dimensions, what we have is that h in 1D, we will have that h is of the form of a trigonometric function of with this speed. Okay, so we can have like something like a cosinus by a certain frequency that we will have by the square root, okay, minus so the propagation of a wave with a given frequency and a given wavelength. Okay, so we have look with some coefficients in here and the same for the sinus. Okay, so solutions of this type, right? Where in fact the speed will be given by these two constants that we will have in fact here. Right, so this is the two of them are exactly given by the same wave equations that can be isolated with the speed given by in the wave equations that we have is this is what we have is c square here. The second time derivative will be given by our c square with a given delay we'll have here. We can derive the omega. In fact, we'll have k in this case that we have here. Our c will be like this omega according to the units. We have omega k. We have k 1 over k omega over k for this case. That's good. So we will have something similar here relating the second derivatives, and that will be our speeds. Right. So to do the parallelism with the wave equation. So these equations are hyperbolic equations, but they are linear. Okay, which makes things a little bit easier to deal with than what we had before with, for instance, Navier-Stokes. Right, being said that, okay, so we have this divergence-free condition, which means that this constant is not equals to 0, but if the initial condition we have divergence-free, so it will be divergence-free, okay, everywhere, and throughout time as well, okay. And we can write in that manner. Okay, we have a little bit a closer look at how the our equations look like. So we have as our unknowns as we had here. So u equals as epsilon e and mu h, and we have a look at the form of the equation. So we have it's equal to the rotational of h, and we want to write this rotational of h as the derivative of a given function with respect to x1 plus the derivative of the second function with respect to x2 and plus the derivative of a given function with respect to x3, right? So we can, this is a way of writing the rotational in that manner. So we would have that in the first case, okay, we have derivatives with respect to x1. We will have just, in this case, in the second component, okay, we will have the h1, in here, but just for the second component, and then derivatives with respect to the f1 that we will have here. So we will have in a second, so with a minus of derivative of h3, doing the rotational that we have here. So we have the derivative of the x1, okay, just appearing for the second component, minus h3, right? Okay, and then also for the for the third component by derivative of h2, and that's 0 here. And for the f2, we will have, in fact, derivative with respect to x2, we'll have for the first component, we will have h for the first h3 in here, and then also with respect to the second component, we also will have for the 0, and then the h in here, okay, and minus h1, okay, and then for the third component, something similar. Okay, we will have for the first minus h1, and then for the second component, it's a bit longer without having it written explicitly. It's a little bit longer, but we will have then also derivative with respect to x3, then minus for the first one minus x2, no, and then also the first we will have positive, and oops, let me get that. And then for the second component we would have h1, if I'm not wrong. So this is a way of writing why we're doing that. So this means that our u is divided by epsilon, so the f1 would need obscene this divided by mu, okay, because if we want to write it as derivative of u with respect to time plus the sum of derivative of fi with respect to xi, we will need to have it in that manner, our f1, f2, and f3. Okay, so if we have this equal to 0, it means that we have with the opposite sign the other time, so there will be minus f1, minus f2, minus f3, right? So this is what we have on the slides. We'll have minus f1, and minus f2, and minus f3, because this is going to the opposite side, okay, as we have it in that manner. So we have minus f1, minus in this case, and minus in this case. So you have much more better written, much clearer, in fact, on the slides, okay, which we have the first three components. That should be what I have written there, h3, h2, but with a minus, okay, that we had because they are in this component. So why this form? It is called conservative form because then when in fact these f are linear with respect to our variables, in the second block we have exactly the same thing but with the opposite sign, because in here I remember that we have mu by derivative of h with respect to t, it's equal to minus the rotational with respect to e. So for the second block, we should have exactly the same thing, but with h replaces by e and with a minus sign. Okay, and that's what we do have. So the nice thing of this is that this f is linear. The equations are hyperbolic equations and they are linear. So this can be written as a matrix multiplied by the same u. Right. So we can have as derivative of u with the two components. So f, as we said, we'll have this and the e3 and e2. Okay, and then with a minus e3, c2 and e1, and then this the second three components will be like that. Okay, then we'll have e2 minus e1 and e0, and these are dfs that can be written as a matrix. Note that my f1, I can build it as a matrix by f1, where the matrix is constant. Okay, in this case, my matrix, sorry, I didn't mean f1 by the same u. Okay, by my unknown, which contains u and e. So by having e as a matrix, okay, which is going to multiply my h, so it's going to be the first row is going to be zeros, okay, and then 1, 2, 3, 4, 5, 6, and I have a minus h3, so all zeros, and minus 1 in here, but divided because my u in fact contains a mu, so 1 divided by mu in this case, and then zeros, all zeros, and 1 divided by mu here as well. Okay, and all zeros in the first. And then for the E3, so something similar, 0, 0, and 1 over the epsilon, and because there's a change of sign, this should be a minus, and we have 0 minus 1 over the epsilon and 0. We have a big 0 here, and this is also a big 0 here. Okay, so it's larger to explain than to guess what we are doing. So we have these blocks and this block here, but that will be my A1. And similarly, we have for the F2, we have different matrices that multiply U, and the same for the vector F3. And this allows to have this conservative form into something that looks like AK by the derivative of my U with respect to xk. Okay, the A's are constant, they depend on the material parameters. Okay, and this is another way of writing exactly the same Maxwell equations. Okay, but these are Maxwell equations, okay, in conservative form. Okay, why this advantage? So you know that this looks like these conservative forms. We can use the concept of characteristic lines. The characteristic lines are those that have the speed of AK. In this case, it's not an actual material or spatial speed, is the one given by this AK. Okay, that is where the information does not change, where my U is constant, okay, along the characteristic lines. Okay, so that looks like the spatial time derivative. Okay, with spatial velocity a. Okay, instead the spatial velocity, okay, is not exactly spatial, but is a velocity where u is traveling. Okay, that is transforming my spatial velocity with respect to the material time velocity. So is along these lines where my unknown u is not changing. Okay, and this allows to interpret, okay, what is happening, and also numerically is maybe also advantages. We will go back to this form later on, but so far let's keep that in mind, that we can also write in that form with a linear function fk. okay, and the sum. So it's another way of writing our rotationals. If we have electrical charges and with some conductivity, then we will have this first term on the right hand side. This is something given by the presence of these charges, but it's not in our depends on you as well, but this is given by the environment that we are studying, but it's first order hyperbolic equations that we have already seen some of the tools when we were using Euler's equations. In fact, they are far simpler. Euler's are nonlinear, and in this case they are linear for the structure of this F that we have here. So we can reduce these equations, and that's the aim, the Maxwell's equations that we have in here, and try to see what does it happen if at least along one direction things are constant. By things we mean my electrical field or my magnetic field. These are the first set of Maxwell equations, the first block, where we have the time variation of my electric field, and these are for the magnetic field. So variations along Z, they vanish. In fact, it means that I can cancel this term here. All derivatives with respect to Z, I can get rid of them, right? So in other words, we have some simplifications and look a little bit simpler. I can in fact here try to join unknowns that are coupled from others. So in fact, this set of 6 equations, the same that I have, I can divide them on those that where E1 is appearing, like here, E2 and H3. And I get this set of equations. So I get this one here, and another one for H3. And the others where I have my H1, H2, and my A3. And then I get these equations, and that equations. So these two, this set of 3 equations are uncoupled from these 3, but in each of them, magnetic and electrical field are coupled. What does it mean, this transverse electric and transverse magnetic? We have done the derivatives with respect to Z equals to 0. So in fact, we are looking at the solutions where along my Z direction, and I have my X and my Y, that will be along my Z directions, things do not vary. So whatever I'm solving on that plane is the same happening on all the planes. So I have the solution around here, and in all the other planes exactly the same that is happening on that reference plane. There is no variation along Z. And I can either study my transverse electric contains E1, E2, and my also H3. So in other words, I have my E1 as an unknown, E2 as an unknown, and my H3. H3 does not vary along Z, but it varies along time, right? So I have H3 with respect to time depends on E1 and E2 with respect to X and Y. So all of them change along time, none of them change along Z, but they vary along X and Y. And there's a set of equations similar to Maxwell's equations, but only defined with on a plane without any variation along Z. So this is the transverse electric and the transverse magnetic, where we have split this set only with H1, H2, and E3, which couples the first component of the magnetic field, the second component of the magnetic field, and the third component of the electric field. So I can the two of them have the same structure. I can either solve this one or this one. It's going to be very similar. The only is my material constants that are varying here. So I have time derivatives of E, and here then I have my minus, so it's going to be reversed with respect to Y and X, and with different material constants. So I have in fact that as if my E3 would be my minus H3 here of the transverse electric. So one is transverse with respect to the magnetic. So this is transverse electric because, okay, in the plane I'm working with E1, E2, and magnetic because of the plane I'm working with H1 and H2. But, okay, very similar extraction, one looks like reverse with respect to the components H1 and H2. And I choose to solve one of them, no need to solve the two of them. They're going to have the same features and qualitatively going to be the same. It's only the material constants are going to be different. I can now go a little bit further and say, what does it happen if, in fact, nothing varies along y? Okay, so if nothing happens along y, so it means that I can rid of this derivatives with respect to y and also of derivatives with respect to y. And what I'm left with, okay, and that would be going from 2D to further going to 1D. So as if I have my derivative with respect to y equals to 0, and I get my derivative of my E1 that I had here with respect to time. This is going to be equals to 0. Okay, that's what we had here, no y derivative. And my derivative with respect to E2 is going to minus H3. Okay. With respect to x. And very similarly, I have my mu derivative of H3, and my y is going to be cancelled here, and I just left with the E2, minus derivative of E2. Right, so this, what I've gone from 2D to 1D to the transverse electric, and this what means is that I'm no variations along y, no variations along z, there's only variations along x. Okay, and E1 is constant. Okay, my E1 component is going to be constant, and I have variations of E2 and H3. So in here, I'm going to work like a wave that is advancing along this direction. Okay, the two components E2 and H3, they are going to vary, and according to the variations of the E3. So this, in fact, E2 varies according to how H3 varies in space, and the time variation of H3 varies according to the space variation of E2. So this is what we were, in fact, looking at this previous slide, like that one, okay, where the two, the magnetic and electrical field are coupled. So we can simplify the equations, okay, and going to much simpler. This is E1 equal constant, and having a set of equations between E2 and H3. Okay, but still, even if we go to 1D, the electric field and the magnetic field are coupled. Okay, in any reduction that you may use. Similarly, we can do the same with the transverse magnetic, the same reduction to 1D, and we end up by working with my H2, E3, and my H1 equal to constant, and a similar plane where my H1 along this direction, and I have, okay, my E3 and my H2 here. Right, so the two types, the data simplification of a propagating wave, where the speed, the two of them are coupled. So we see, in fact, here we do the time derivative and the space derivative of this equation. We have one wave equation for E2, and we can do space derivative and time derivative of this one, and have also another wave equation in terms of H3. Okay, so in fact, from the transverse electric, we can have the 1D equation of the wave that we have just deduced. So we have E by mu and second derivative of E2 with respect to time. Okay, that should be equal, let it process, okay, to the sorry, here we have this E2. So it's a wave equation just on the E2. It's a propagating wave, and something similar, exactly the same equation for H2. And the same will be happening for also for this for H3 in the transverse electric. Okay, and for the transverse magnetic, wave equation for H2 and for E3. Similar by doing this reduction, okay, or the derivatives on time and space, and crossing similar terms. So with that, okay, it's clear how we have gone through those simpler cases. They are always coupled, okay, in transverse electric and transverse magnetic, and in here you have also a derivation of going to the wave equations, which in 1D is just double derivative with respect to x, as we would have. All right, so this is the equation, so we are now familiar with them, and we would like to solve, okay, this system, the wave equations. One way is to deal with time harmonic solutions. So we have the electric field and the magnetic field. Let's assume that we are working on a given frequency, omega, and that my solution is a given component that changes in space, but my dependence on time is oscillatory according to this harmonic function, exponential of I omega t. Okay, so all the time derivatives are going to be affecting this harmonic term, and in fact my spatial derivatives are going to affect only my field E0, which becomes my unknown. Right? Doing this wave equation with this assumption, then we end up by Laplacian of epsilon 0 plus the omega square with I square. So this becomes a minus here, which becomes a plus, and then we get this equation, which is Helmholtz equations. Helmholtz equations for my electric field and Helmholtz equation for my magnetic field. And note that there is an assumption that is the omega, okay, the hypothesis that we're doing, that there's a given frequency. But we can aim at looking at my waves, my oscillations in space for this frequency. Okay, and now it's a little bit simpler because we have just dependence on differential operators just on space, and with an unknown that only depends on space. It's simpler a priori, but also there's some difficulties when we try to work with a numerical solution of these equations, and that may be that we may have some singularities depending on the domain. Okay, depending on the shape that we have, there's no always easier to solve them, right? So this is one example of the L-shape problem, where the analytical solution in fact can be written in terms of these Bessel functions. Okay, these Bessel functions, there's a series of them, and the solution is written in terms of the sum of this series of Bessel functions. When we work with derivatives, and our electric field is a derivative of this Bessel function with respect to y and with respect to x, like the rotational into of this f function I will have here, and will be like the normal component of the electric field here, and then the rotational of that field itself will be my magnetic field. Okay, and because of the harmonic assumption, we don't have the time derivative, and the time derivative of H, this is the Maxwell equation for the magnetic field, but with the time derivative has been replaced by I omega with a minus. Okay, and that would be what we would get as the resulting equation. So with that, when we want to write the analytical solution, we just need this f. But this f is, in fact, depending on this Bessel function and the series of them, and we would need to have derivatives of this Bessel function. In fact, we have e is the first derivative of f, and here we have an additional derivative. So in fact, our magnetic field includes second derivatives of this f. Working in radial notation from that point, okay, we have the radial derivatives, okay, working in polar coordinates. So in that case, we will need the Bessel function itself for alpha equals 0, for alpha equal other values. Okay, for alpha equals 0, the first derivatives and the seconds, they behave well and they are bounded, but the second derivatives of the Bessel functions for some alphas, in fact, they are unbounded. Okay, and this reflects the singularity of the magnetic field at this point. This, when we work with a discretized problem, so we get a numerical solution that, of course, cannot capture, it's not going to capture exactly the singularity that we have at this corner. And this may pose, okay, a problem if we try to discretize with a finer and finer mesh on that corner. Okay, that the solution gets. We are not solving in a pointwise manner with finite elements. We build a weak form. So in fact, even if there's a singularity, we circumvent it because we are doing the integrals of our solution and building on the weak manner. But the smaller the element we might be using here, okay, the worse and the higher the value that we may get. So in fact, we may not have interest in getting very, very small and very fine mesh at this point, unless we do some averaging here. Right, so this poses the difficulties of the Helmholtz equations that is being illustrated in this type of problem. So let's try to look at some of the more practical applications. Okay, one is the direct problem on scattering. That is, I have an object. I know the object exactly how is the boundary, and I'm interested in sending incoming wave, which means an electrical and magnetic field, either of the two, working in one 2D. So on the transverse electric or transverse magnetic, and checking how is the reflected wave that we have here. Okay, and then just solving and trying to get very accurately how is the magnetic or scattered magnetic electrical scattered field. The inverse problem, which is more interesting, in fact, from engineering perspective, is I don't know the object, but I want to detect it because I have the scattered field, and I want to know which is the size or the orientation of this object. Okay, this, as we have already mentioned, has applications in biomedicine, also not only in aeronautics, but so it's a bit more difficult because the solution might not be unique. Similar or very similar scattered fields may be due to different objects. Okay, so it's the inverse problems, and inverse problems usually they don't have a unique solution. Okay, determining the shape, so we may get something closer to the shape, and to make things worse, inverse problems, they may not be well posed, not having a unique solution because we have different, then they need to be regularized. Regularized, it means to add some terms in our equations so that we get a unique solutions, right? So we'll deal with direct problem, okay, and knowing that from those direct problems, okay, we may be able to solve the inverse problems. Right, how these problems are faced. So we split our electrical field into the incident wave that we have going to the object and the scattered field. Okay? And this is known, so the incident wave is known, and what we can measure, in fact, might be our global solution, which is the sum of the incident and the scattered field. So we may try to solve for E or just for S, okay, knowing that what we are measuring, in fact, is the sum of the two. Okay? So we know that the incident wave is a solution of the Maxwell's equations in void because it's coming from, let's assume, from the infinite, but where our object and obstacle has a different material property, like this one. Okay. So we know that E and H should solve our Maxwell equations, and the incident wave should also solve Maxwell equations in the empty space or with these epsilon sub 0 properties. Okay. Otherwise, we know what we are saying is that that we have mu 0 with respect to TD is with regard to the incident wave, and the same similar equation is also occurring for the incident wave, also for the electrical field, right? And for the total field is also satisfying our equations, but instead with a mu, which is where the obstacle is, the material properties where the obstacle is placed. And with H. So if we use the fact that my scattered field is equal to the total minus the incident, and this is true for the electric and the magnetic field, okay, we can split this term and do the subtraction of the two sets of equations, okay, for the scattered field. Okay, for instance, we can do this equation minus that equations, so what we have on the right minus what we have on the left, and we'll have derivative of h with respect to time of mu minus mu 0. Okay, it's equal to minus for the scattered field, okay, and the same, okay, for the epsilon also here. Okay, so we have in this is an E, for the incident field equal to the rotational of our magnetic field scattered, which is the difference of H minus Hi. Right? So we can further write as the sum here H of Hi minus Hs, and putting on the right hand side everything that is known. Right? So in total for the first equation, so writing that mu derivative of H with respect to T, and having here the incident, plus mu derivative of H with respect to T of the scattered, minus mu 0 by the incident with respect to time equals to the rotational of the electric scattered field. So this is our known, and we can place this term and this term, I mean this one here, on the right as a source, okay, as a source of our knowns of the incident waves, and write equations in terms only of the scatter. So by doing that, that's why that's where this is coming from. So the difference between the two writing equations only in terms of the scattered field, and having additional terms on the right? And trying to solve only for either what is being measured or either for the scattered one. Okay, so at the end it boils down to only having additional terms in the source term on the right, even when we don't have any conductivity. Right. And with that, this is known, and that's for solving the direct problem um, in the scattered problem. Then we can do exactly also the same thing that we had. So doing the time harmonic steady state. So that depends on omega, and looking at the in fact at the doing the Helmholtz equations only for the scattered field. Okay. So we solve, and the steady state should at the end should vanish these terms, and only having a Laplacian. That's what we are doing for a given omega. Okay, the Laplacian of our that we have in the Helmholtz equations. Okay, so this may be sufficient to solve some of the scattering problems for known. Okay, for known problems of the scattering done by the clouds. Okay, we have the presence of the clouds, and the field is being scattered by the presence of the cloud as an obstacle. And depending on the position or the length it has to cross on the atmosphere, okay, so when it's blue, it's rather reddish, may depend on how much the waves have to cross. So if this is the atmosphere, and this is the Earth, okay, whether a wave have to go through a longer path than when they come to through the top. So because some waves are being scattered and others are being absorbed, so here there's a longer path for being absorbed, and there's only the red, which is the infrared part of the visible light that is being. Okay, so so those that are being absorbed, depending which one are being scattered, matters for for instance, for the color of the sky that we see. Right, there's other practical applications for the scattering problem. One we see is looking inside, so looking how the waves are being scattered. Okay, and this is rather the inverse problem. So we don't know the obstacle, the shape, or whether we may find anything at all here, or in fact whether which is the shape of the obstacle. Also for determining the presence only of an obstacle, how the field is being perturbed. So the scattered field that we have reaches the camera, so in fact it's not visible. Is not a picture that they do. They do also a picture, but in fact they work with electromagnetic waves. The same for the weather forecast. Satellites, they don't do pictures, but in fact they analyze the light that is being scattered, okay, from the Earth. And by the analysis of this light and how is this scattered field, we know which detect the presence of some clouds or different properties on the atmosphere. Right? So this was also on the news when this was released. The first scanners that allows to really go in detail of the obstacle. Who says obstacle says a body, and then it's like you go watching through. This was around 20 years now, okay, but this was so when the first inverse problems could be solved, it was a big news release that was sent. All right, we will deal with the boundary conditions, how to solve in order to go to the numerical problems. We will have to set when we have the equations, so the partial differential equations, but we need to also say something about which type of boundary conditions. So depending if they can transmit, whether electrical waves can be transmitted or the magnetic waves can be transmitted, and there are objects that in fact can prevent one of the two. Okay, For instance, in a car, so how the waves that we have inside, how it reaches, so it's different depending on the shielding that we may have. So with that, we finish the first session, and we'll have a second session looking at these boundary conditions and looking at the numerical solutions that we have for these electromagnetic problems. Thank you, and looking forward to see you in the second session.